The laboratory is led by a Dutch professor, Teun Klapwijk, who will be also staying with us for another 2 years as a professor of the Division of General and Experimental Physics. And behind me you see one of the biggest pieces of equipment in our laboratory. It is a dilution refrigerator that allows us to make measurements at unprecedentedly low temperatures, much lower than the temperature of liquid helium.
If you now go to the superconducting state, there is something which BCS had predicted, and it is much too technical to go into details now on that, but you have an energy gap. And the reason is, if you have electrons attracting each other, and you go to a state where all these electrons become a pair, then there is binding energy between them. So in order to get free electrons, you have to break those pairs. Now that breaking of the pairs is this energy gap.
In our institute, we can give for the students, first, of course, lectures and practical education in physics and in English, but also some technological education in our nanolaboratories and also in our startup companies.
First of all, it's a great pleasure to work with your students and participate in this collaborative program, since I guess we've been doing this for more than 10 years now.
I think I got a unique possibility and unique experience here. So in addition to regular, good level physics and math, during my last 2 years on bachelor program, I got experience in experimental physics. Not in so many places you can get this experience. And of course, during my master's degree, most of the time we spent in experimental labs.
And I should say that the level of preparation, the background level of Russian students coming from your institution is extremely competitive. We've been happy to use your excellent devices that are the best in the world still. The superconducting photon counters.
I think I was very lucky when I was on the third year of my bachelor program. One of the professors of physics invited me to work in the lab. I still remember that day, when it was my first day in the lab. It was something mysterious for us. I got my bachelor, master, and PhD in physics, but in addition, we studied chemistry, biology, history, which you never will meet in other American universities. So right now, for example, I work in their biomedical lab, which doesn't have physics even in the title of the lab. We're working on molecular aging, and knowledge I got here allows me to work and move from one division of science to another one. So pretty flexible.
My name is Ekaterina. I'm from Moscow. Really, I like studying here. It's my home, second home. I really think that my department is the home for me. And I decided that I will go to this university and I will become a teacher of physics.
I want to talk about single molecules. I hope you can see that. The contrast is not quite as high as one might like. But after nearly 30 years, since 1989, what's new? That's my goal for my lecture today. I want to talk briefly about the early days of single molecules, and then about single molecules as local probes, or nanoprobes, of metallic nanoantennas. Then talk about super resolution microscopy with single molecules. And then talk briefly about low temperatures once again, super resolution with single molecules at low temperatures, actually a red photoactivatable fluorescent protein. Then three-dimensional imaging can be achieved using point spread function engineering. So I'll describe some new results in that area, a tilted light sheet design, and then also show that you can do three-dimensional tracking as well as super resolution in the same cellular system to explore interesting biological problems mention accuracy. There's been a lot of talk about precision, but not so much about accuracy of single molecule localizations. And then finally, talk about single biomolecules in solution. So this is a long list of interesting new developments, and I want to present most of them because different people in the audience may find resonance with different examples, whether they come from chemistry or biology or physics.
Repeat some key ideas. So one of the things that we discovered over again and again in the 30 years since we are looking at single molecules is that nature is much more complex and interesting than we ever thought, even at that time before this single molecule experiment started. And one of the things, of course, blinking and dynamical heterogeneity are one of the surprising big discoveries that still need to be explained and understood better and maybe used for some application in the future. Plasmonic sensing and all plasmonic effects, we have seen that this is extremely powerful to make molecules that would otherwise be invisible, to make them easily observable, and you can then study them. And with nanobubbles and other phenomena on small scales, you can repeat all kinds of experiments that were done in microscopic physics now on small and small scales, and either make smaller devices, nicer applications, but also understand better the interactions of molecules and structures on nanometer scales.